Hi friends, in this video we are going to learn about properties of eigenvector. So here the first property said if x is a non-zero eigenvector of A with corresponding eigenvalue lambda, then kx, where k is non-zero scalar, kx is also an eigenvector of A with corresponding same eigenvalue lambda. So here what is given, we have to show this kx is also an eigenvector of this matrix A with corresponding eigenvalue lambda. So here what is given information, here given lambda is eigenvalue of A with eigenvector x which is non-zero. That is given information. That is here ax which is equal to lambda times x. Here suppose of course x is non-zero. This is equation number 1. So here they are saying kx is also an eigenvector. Since k is non-zero, therefore since k is non-zero, this implies kx, k times x, which is also a non-zero eigenvector. So kx is also non-zero. So here also non-zero. Therefore here multiply k on both side of equation 1. So what will happen here? Here this is k times ax which is equal to k times lambda x. So here this is, I will write here a into k times x which is equal to, here I will write here lambda times here k times x. So here this means that kx is a eigenvector of A with eigenvalue lambda. So that is our proof. Here this is our proof. Here they are saying if x is the eigenvector of A with eigenvalue lambda, that is x equal to lambda x. This means lambda is the eigenvalue of A with eigenvector x. Since x is non-zero here and k is non-zero, then kx is non-zero. Then multiply k on both sides to this equation, we will get this equation. This means here a times kx equal to lambda times kx. This means that this kx is an eigenvector corresponding to eigenvalue lambda of the matrix C. So now this is second property. Here x is an eigenvector of a matrix A, then x cannot correspond to more than one eigenvalue of A. That is, here they are saying if let's say A is one matrix and here lambda, here this is lambda, x is a eigenvector corresponding here. This means that, so if I write here ax equal to lambda x, here lambda is the eigenvalue of a matrix with corresponding eigenvector x. They are saying if x is an eigenvector, then x cannot correspond to the two eigenvalues lambda 1 and lambda 2. If at all, assume if lambda 1 is the eigenvalue of A corresponding to the eigenvector x, and if I take the another eigenvalue, let's say lambda 2 is the another eigenvalue of a matrix A with corresponding eigenvector x, then these two eigenvalues are actually same. This means that if x is an eigenvector of A, then x cannot correspond to more than one eigenvalue. That is, corresponding to each eigenvector have one eigenvalue. If at all, if we assume that let's say two eigenvalue, these two eigenvalues are actually same. That's we have to prove. So here what is given information? So here they are giving here x is an eigenvector of a matrix A with eigen, let's say let lambda be an eigenvalue of A with eigenvector, let's say eigenvector x. So of course this is non-zero. That is ax which is equal to lambda times x. So this is the given information. So here I am assuming, here assume lambda 1 and lambda 2, that is lambda 1 is not equal to lambda 2 are the distinct eigenvalue of A corresponds to x, non-zero eigenvector. So corresponds to x, eigenvector x. That is ax which is equal to lambda 1 x and ax which is equal to lambda 2 x. So here lambda 1 is the one eigenvalue corresponding to eigenvector x. This is lambda 2 is the another eigenvalue corresponding to the eigenvector x of a given matrix A. So here this is my equation, let's say 1, and let's say this is my equation 2. The left hand side of this equation 1 and equation 2 are same, that's the right hand side must be same. Here I am taking lambda 1 x which is equal to lambda 2 x. Here I will take here lambda 1 x minus lambda 2 x which is equal to 0. So from here lambda 1 minus lambda 2 into x which is equal to 0. Here product of the two value is 0, either one must be 0. Since x is non-zero, that lambda 1 minus lambda 2, that is this term must be 0, that is lambda 1 minus lambda 2 equal to 0. This implies that lambda 1 equal to lambda 2. So here this means that x cannot correspond to two distinct eigenvalues, lambda 1 and lambda 2. This means here this is equal to lambda 1 equal to lambda 2. This is contradiction. So this is the contradiction. This is the upset result. By we are assuming that we have two eigenvalues corresponding to the same eigenvector lambda 1 and lambda 2, such that lambda 1 is not equal to lambda 2. So here we got lambda 1 equal to lambda 2. This is contradiction to this distinct eigenvalue. Therefore x cannot correspond to different or distinct eigenvalue. Therefore, so this means that x cannot correspond to a distinct eigenvalue of matrix A. So that's we have to prove. This result said that if x is an eigenvector of A, x have single eigenvalue corresponding to each eigenvector x. If at all, if you are taking two eigenvalues, let's say lambda 1 and lambda 2, that two eigenvalue must be same. So that's we have to prove. Now this is property 3. So property 3 says the eigenvector corresponding to the distinct eigenvalue of a matrix are linearly independent. In last property says if you have one eigenvectors, so corresponding to each eigenvector we have single eigenvalue, so of a square matrix A. So here this result says, for example, let's say you have two eigenvectors. Let's say this is v1 and let's say this is v2. So here let's say v1 is the one eigenvector and v2 is the another eigenvector, and this corresponding to v1, let's say I have one eigenvalue lambda 1, and corresponding to v2, let's say I have another eigenvalue lambda 2, and they are saying these eigenvalues are distinct. So eigenvectors corresponding to the distinct eigenvalue of a matrix A are linearly independent. So here v1 is the eigenvector corresponding to lambda 1, v2 is my second eigenvector corresponding to the eigenvalue lambda 2, and this eigenvalue lambda 1 and lambda 2 are distinct. This means they are not same. So I want to show this v1 and v2 are linearly independent. Here I want to show this v1 and v2 are linearly independent. So first we have to know what is meant by linearly dependence and independent. So here, so first I will explain quickly definition. So for example, let's say I will quickly here linearly dependent. So what is meant by when we say that the two vectors are linearly dependent? Let's say v1, a set of vectors, that is v1 comma v2 is said to be linearly dependent. So there exists a scalar, let's say c1 comma c2, such that here c1 comma c2 not all zero, such that c1 v1 plus c2 v2 equal to 0. So here if these two vectors v1 and v2 are linearly dependent, their linear combination, that is there exists a scalar c1 c2 not all 0, such that at least this means either c1 is non-zero, c2 is non-zero, or both c1 and c2 are not 0, such that their linear combination c1 v1 plus c2 v2 equal to 0 and linearly independence. So what is meant by linearly independence? Linearly independence. So when we say that that the two vectors are linearly independent. So for example, the set of vectors, let's say v1 comma v2 is said to be linearly independent. There exists a scalar, let's say c1 comma c2, for which c1, let's say this is c1 v1 plus c2 v2 equal to 0, then ci equal to 0 for all I. So here the basic difference is, for example, let v1 and v2 are said to be linearly dependent. There exists a scalar c1 c2, not all 0, means at least one of the c1 is non-zero or c2 is non-zero, or both c1 and c2 are not zero, so that their linear combination is 0. So that is at least one of these ci is non-zero in case of linearly dependent. If in case of linearly independent, if two vectors are linearly independent, there exists scalar c1 c2 such that c1 v1 plus c2 v2 equal to 0, then all ci's are 0, means c1 is 0 and c2 is 0. This means that these two vectors are linearly independent, and this is the case when two vectors are linearly dependent. So for example, so in R2, so for example, if I take here, so let's say this is my v1, let's say this is my v2. So here I will take this coordinates are 1, 0. So here I am taking 0, 1. Here 0, 1. So here you can observe one thing. Let's say my v1 is 1, 0 and v2 is 0, 1. These two vectors are linearly independent. So here I will show. Let's say let c1, c2 belongs to, let's say, R2, such that let's say c1 v1 plus c2 v2 equal to 0. Here I will show c1 is 0, c2 is 0. Here my v1 is 1, 0 plus c2 here 0, 1, which is equal to 0. So here this is same as c1 0, this is same as 0, c2 which is equal to 0. So here this implies here c1 plus 0 equal to 0. Here this implies 0 plus c2 equal to 0. Here this is matrix. So here this implies c1 equal to 0, this implies c2 equal to 0. So here v1 is my one vector, this is here unit vector along x axis, and v2 so is my another vector, unit vector along y direction. So positive direction of y axis. So here I am taking c1, c2 belongs to R, so that c1 v1 plus c2 equal to 0. Here c1 into v1 plus c2 into v2. Here v1 value is 1, 0. Here I just put value. Here I multiply c1. So this is equal to c1 plus 0 equal to this 0. 0 plus c2 equal to this 0. This implies c1 equal to 0 and c2 equal to 0. This means that these two vectors are linearly independent. So v1 corresponding to lambda 1, v2 corresponding to lambda 2. Lambda 1 and lambda 2 are not equal. I want to show v1 and v2 are linearly independent. So here let v1 v2 are the I am proving these results in case of two vectors. We can generalize for any. Here two are the eigenvector with corresponding eigenvalue lambda 1 and lambda 2 respectively. So here distinct. So respectively, of course, this lambda 1 and lambda 2 are distinct. Here these are the distinct eigenvalue. So here why respectively means lambda 1 is the eigenvalue corresponding to v1 and lambda 2 is the eigenvalue corresponding to v2. So here this means that a times v1 which is equal to lambda 1 v1 and a times v2 which is equal to a is linear operator and lambda 2 v2. This is the given information. I will give it as 1. This is my 2. So I want to show this v1 and v2 are linearly independent. So my aim, we have to show to show V1, V2 are linearly independent. So, but assume, so by contradiction, assume these two V1 and V2 are linearly dependent. So my aim is to prove this V1 and V2 are linearly independent, but here I am taking these two vectors are linearly dependent. Here I am saying assume, so we are going to by contradiction, assume V1, V2 are linearly dependent. So if V1 and V2 are linearly dependent, so here I will quickly explain what is meant by here. So while discussing here, C1, C2 is my scalar, V1 and V2 are the vectors. That is C1 V1 plus C2 V2 equal to 0. Here at least C1 is non-zero or C2 is non-zero or both C1 C2 are non-zero. So at that time we can say these two vectors are linearly dependent. Here I am saying, here I am taking this my C1 is non-zero and C2 is non-zero. Here I am assuming at that time what will happen? C1 V1 equal to minus 2 times C2 V2. So this is same as V1 equal to minus C2 by C1 times V2. So this is V1 equal to, so let's say some k times V2. So this means that one vector is the multiple of another. So here in case of linearly dependent. So here I am taking V1 and V2 are linearly dependent. Here I am assuming, let's say, let V1 equal to, let's say, some k times V2. So here of course this k is non-zero scalar. So of course this k is non-zero scalar. Now apply. So now apply A on both sides to this. So what will happen? A times V1 equal to, here just this is A times k V2. So here which is equal to, here I will take k A times V2 which is equal to k, here A V2 is here lambda 2 V2. So here AV1 is equal to, here I got AV1 which is equal to k times lambda 2 V2. Let's say I will give this as 3. Since V1 is also a non-zero vector, now so this is my equation 3. Now so since V1 which is a non-zero eigenvector, therefore A V1 which is equal to lambda 1 times V1. So which is equal to lambda 1 times, here put the value of V1, here I am taking this is k times V2. So which is equal to lambda 1 times k times V2 which is equal to here, so this is A V1 equal to here lambda 1 times k times V2. Let's say this is my equation number 4. Now from equation 3 and 4, so from equation 3 and 4, so here from equation 3 and 4 what we will get? Right hand side are equal, that is this is equal, left hand side of these two equations equal, so right hand side must be equal. Lambda 1 k times V2 must be same as k times lambda 2, this is V2. So here I will take this as left hand side, here lambda 1 k V2 minus lambda 2 k V2 equal to 0. So from here can I take here lambda 1 minus lambda 2 into k times V2 which is equal to 0. Since my k is non-zero, so here where this my k is non-zero and V2 is one eigenvector that must be non-zero. So if k is non-zero, V2 is non-zero, this must be here lambda 1 minus lambda 2. This product must be, this term must be 0. So that is lambda 1 minus lambda 2 equal to 0. This implies that lambda 1 equal to lambda 2. So here which is contradiction to this. So here which is contradiction to this. That's why these two vectors, therefore V1 and V2 are linearly independent. So that's we have to prove. So property 4 about eigenvector says eigenvector corresponding to the distinct eigenvalue of a real symmetric matrix are orthogonal. So what is given information? So matrix is real and symmetric. So what is meant by A equal to A transpose? This means my matrix is symmetric. So that is the given information. And so here let's say I want to show these two vectors are orthogonal. Let's say x1 is the eigenvector corresponding to the eigenvalue lambda 1 and x2 is the another eigenvector corresponding to the eigenvalue lambda 2, and these two eigenvalues are distinct. I want to show this x1 is perpendicular to x2. That is meant by these two vectors x1 and x2 are orthogonal means I want to show these two vectors x1 and x2 are orthogonal. So when we say that the two vectors is orthogonal, so here if this let's say x1 and x2 which is equal to, that is x1 x2 cosine of the angle between 2. Here if theta is 90, so if theta is 90 cos 90 is 0, so therefore x1 x2 which is equal to x1 dot product x2 cosine that is 90, so which is equal to cos 90 0, so this is 0, so x1 x2 equal to 0. So but here, so I want to show the dot product of, that is x1 into x2 is 0, the product of these two vectors x1 and x2 is 0, but here this direct product that is not possible. So I have to take here let's say this matrix. So here, so from here can I write here, so A x1 which is equal to lambda 1 x1. So with this I will write here A x2 which is equal to lambda 2 x2. So here let's say this my matrix A is of order, let's say here I am taking n cross 1 and this x here I am writing corresponding to this. So here this x is of order, let's say of dimension n cross 1 here. So here of course this is n cross n. So this matrix is of order n cross 1 and this column vector is of order n cross 1. So this matrix multiplication is possible in between A and x. In the same way here I am taking A, so is of order n cross n and x2 is of order here, let's say column vector is of order n cross 1. So this matrix multiplication is also possible, but here it is, but this is not possible. Here this is x1 is of order n cross 1, but and this product between x2 is of order n cross 1. So if this n is not 1, so this n and this n is not 1, this multiplication is not possible. So why? Outer dimension of this vector x1 is not same as the inner dimension of this x2. So this is not possible. So I have to take either x1 here, x1 n cross 1 x2 transpose. So this becomes 1 cross n. So or x1 transpose. If I take x1 transpose, it becomes 1 cross n and this is x2 as it is. Here this is x2 is n cross 1. So then this is possible. So this multiplication is not possible, but this is possible. So here this is multiplication of vector x1 and x2. Here I am saying if these two vectors are perpendicular to each other, then their product x1 x2 is 0. So I have to show either x1 into x2 transpose equal to 0, or we can show or x1 transpose into x2 equal to 0. So my aim is to prove either x1 into x2 transpose 0 or x1 transpose into x2 equal to 0. That is my aim. So here how to prove this I will show here. So here what is given? So here given information is let x1 and x2 are the non-zero eigenvector with corresponding distinct eigenvalue lambda 1 and lambda 2 respectively. So that is the given information. Here lambda 1 is the eigenvalue corresponding to x1 and lambda 2 is the eigenvalue corresponding to x2. That is here if I write ax1 which is equal to lambda 1 times x1 and let's say this I will give this as 1 and x2 which is equal to lambda 2 times x2. This is my equation 2. Now I have to show x1 into x2 transpose equal to 0 or x1 transpose x2 transpose equal to 0. So either multiply equation 1 by x2 transpose or multiply equation 2 by x1 transpose. So either multiply equation 1 by multiply equation 1 by x2 transpose or multiply equation 2 by x1 transpose. So we will get the what you want. So my aim is to prove. So we have to show. So x1 transpose x2 equal to 0, or we can show x1 and x2 transpose equal to 0. So either if you show x1 transpose x2 equal to 0 or x1 into x2 transpose equal to 0. So you have to show any one of this. So here I am multiplying equation 1 by x2 transpose. So here I am going with this. So here multiply equation 1 by x2 transpose on both sides. So here after multiplying equation 1 by x2 transpose on both sides, so what we'll get? Here I will write here. So here, so after multiplying x2 transpose, so this is a x1 which is equal to here x2 transpose lambda 1 x1. So now this is given. Now just take transpose on both sides. So let's say this is equation 3. So take transpose on both sides. So what will get? So if I take transpose, so we know the properties of transpose. If A B transpose is same as B transpose A transpose, or A transpose whole to the power transpose is same as A transpose. Transpose of transpose is simply A. So here I will use this two property. So here I am taking the transpose on both sides. So here x2 transpose A x1 whole transpose which is equal to x2 transpose lambda 1 x1 whole transpose. So this is same as x1 transpose A transpose x2 transpose to the power whole transpose which is equal to here x1 transpose, this is simply lambda 1, this is x2 transpose. So this is transpose, this is a scalar, so no need to take transpose of any number. So here this is not a matrix. Now here this is same as x1 transpose, and since my matrix is symmetric, so here if my matrix is symmetric, A transpose is same as A. Here I am using this property. Here this is x1 transpose is same as this is simply A, this is x2 transpose of transpose, this is simply x2 which is equal to here x1 transpose, this is simply lambda 1, this is x2 transpose of transpose, this is simply x2. Now since x2 is the eigenvector corresponding, x2 is the eigenvector, so can I write this ax2 as lambda 2 x2? So here I am writing x1 transpose, here this ax2 as, here I am writing lambda, here this is my lambda 2 and x2 which is equal to here x1 transpose, this is simply lambda 1 and this is x2. So here can I write lambda 2 x1 transpose x2 which is same as lambda 1 x1 transpose x2. So here I am taking this is lambda 2 x1 transpose x2 minus lambda 1 x1 transpose x2 which is equal to 0. So here lambda 2 minus lambda 1 common, x1 transpose, this is x2, here x1 transpose x2 which is equal to 0. Here you can observe these two eigenvalues, here lambda 1 corresponding to x1, lambda 2 corresponding to x2 are distinct, means here these two are distinct means their difference is not 0. Since this is not 0 means x1 transpose x2 equal to 0. So here this means that these two vectors x1 and x2 are perpendicular to each other. This means this x1 and x2 are orthogonal to each other. That's we have to show. Thank you.